problem.
Switching rooms. This is terrible.
I'm really sorry.
I mean, there's got to be another room that has something better than this little $12. I think 365 does. All right, folks, let's get this show on the road. I think I should have plenty of time to finish. So today we are going to conclude our discussion of the Solow model. Up until this point, we have simplified the model by eliminating exogenous technological growth. So what we want to do is insert that back into the model today. A couple of things I want to mention before we get to the main part of the discussion today. Even the Solow model without technological progress exhibits a property known as balanced growth. I want to talk a few minutes about what that means, because you'll hear me refer to the balanced growth path of a model or its balanced growth state quite a lot this semester. Okay, essentially what we mean by balanced growth is that the main endogenous variables of the model, so things like the capital stock and output and consumption, are all growing at the same rate. So that things like the capital to output ratio or the capital to labor ratio are going to be constant in the steady state if those variables are growing at the same rate. Let me first demonstrate that the Solow model that we've talked about so far does indeed exhibit balanced growth. Aggregate capital, so capital K, should be equal to capital per worker, lowercase k, times the number of workers, right? That's just a rearrangement of that simple identity. Output in the economy is output per worker times the number of workers. Now, we know that capital per worker eventually reaches a steady state in the Solow model, and that output per worker also eventually reaches a steady state for all t greater than or equal to some cap t, which is finite. So eventually we get to a point at which the steady state value of capital and output per worker is reached. At that point then, so for all t bigger than or equal to cap t, we know that aggregate capital is simply going to be equal to the steady state level of capital per worker times L, and aggregate output would be equal to steady state output per worker times L, right? Once we've reached the steady state, we can express aggregate capital and output in terms of steady state capital and output per worker. Now, once we've gotten to this point, let's calculate the growth rates of each of these variables. So what is the growth rate of the capital stock? It's KT plus 1 minus KT over KT. Well, that's just K star times LT plus 1 minus K star times LT over K star times LT. The K stars cancel, and we're left with LT plus 1 minus LT over LT. And what's that equal to? That's just the growth rate of labor, which is equal to N. So you see, once we've reached the steady state or the balanced growth path of the model, the growth rate of the capital stock in the Solow model is just equal to the growth rate of the population. Same with output. YT plus 1 minus YT over YT is just Y star times LT plus 1 minus Y star times LT over Y star times LT. Cancel, cancel, cancel. And that's equal to N. That's what we mean by balanced growth. The main endogenous variables, like output and capital, are going to grow at the same rate. They grow at the rate of the population. And so the capital to labor ratio should be constant at that point. Unfortunately, without, and this is the model that doesn't have technological progress. Unfortunately, in that model, the model is incapable of actually generating sustained growth in per capita output, right? We know that the limit as t goes to infinity of output per worker is equal to Y star. So output per worker eventually settles down to a steady state. This is actually inconsistent with the data. If you look at growth rates of per capita levels of output across the world, even in the most advanced economies like ours, we still have growth rates of per capita output around what, 2% per year, something like that. So the model is missing something from it that would enable it to match that feature of the data, right? Because the model without technological progress just eventually predicts that output per worker will eventually get to a steady state and will no longer change at that moment. So growth in living standards can occur, but only as the economy is transitioning to the balanced growth path or the steady state, not once that steady state is reached. So that's what we want to do today, is think about how we modify the Solow model in order for it to generate sustained growth in living standards in the long run, even after we've reached a balanced growth path. And the obvious way that we're going to do this, you guys are also already aware of this, based on the review exercises you've probably done, is we want to reinsert exogenous technological growth into the model. So that AT that we just assumed was a constant, we're now going to assume that it grows, okay? Here's the key question that we want to ask. How do we model the effects of changes in AT on the aggregate production function? How should we incorporate technological growth into the neoclassical production function? Well, the normal way that is done in macroeconomics is to impose discipline on the form of technology by requiring the allocations that come out of the Solow model to be consistent with balanced growth. So however we incorporate technological growth into the production function, what we want to happen in the end, once we solve our model, is for things like output and the capital stock to grow at constant equal rates over time. We want our technological growth structure to be consistent with balanced growth, because that's what we actually see in the data. If you take a look at long run data for the United States economy, for instance, the capital stock and GDP, real GDP, tend to grow at roughly the same rates over time. Real interest rates tend to be constant. The factor shares tend to be constant, those kinds of things. How do we incorporate technology into the production function in a way that actually delivers balanced growth? That's what we want to think about today, and it will culminate in this thing called Uzawa's theorem, which is what we'll prove. Okay, before I get into that specifically, I want to talk about the different types of what's called neutral technological progress. What types of restrictions does this concept of balanced growth place on the production function? We haven't really made a whole lot of restrictions on the production function yet, right? We've only made two assumptions: that the marginal products are positive, that the second derivatives are negative, so it's strictly concave, and that there's constant returns to scale, and then the Inada conditions, right? Those were assumptions 1 and 2. We were able to prove the existence and the uniqueness and the stability of the Solow model without imposing a bunch of really tight restrictions on the production function. It turns out we will need to impose a somewhat tighter restriction on the production function with regards to technology in order for the Solow model to exhibit this balanced growth property. All right, now to develop this point further, I want to briefly talk about 4 different types of what we call neutral technological progress. It's going to turn out that only one of those types is actually consistent with balanced growth. Just to give you an idea about kind of how you can think about incorporating technology into the production function. The first type is what's called Hicks neutral technology. Let's assume that you have a production function, and I'm going to call it F tilde, that depends on capital, labor, and technology. I'm going to drop all the time subscripts because they're not really important for this discussion. So we know what capital and labor are. A represents technology. Technology is what's called Hicks neutral if we can rewrite this production function as A times F of K and L, where F tilde is constant returns to scale in K and L, and F is also constant returns to scale in K and L. So what Hicks neutral technology does is it basically multiplies the production function by some factor A. To get a kind of a visual description of what this looks like, I'm going to draw something called an ISO production schedule. We do that by mapping all of the different combinations of labor and capital that are consistent with a given amount of output for a specific level of technology. It's going to look something like this. So if technology is, let's say, at A prime, then what this ISO production line shows us are all the different combinations of L and K that produce output Y bar if the state of technology is equal to A prime. Okay? Now, what does a Hicks neutral technological advancement look like? Let's suppose here that technology improves. What that's going to do then is shift in the ISO production schedule so that the same amount of output can actually be produced with higher technology and lower levels of capital and labor. So what this graph shows you is that if technology were to increase, then we can produce the same amount of output using less labor and less capital. That's what Hicks neutral technology does. It allows us to produce the same amount of output using fewer of both of these inputs. Is that clear so far? Is it showing up on your screen all right? Somewhat.
What's that?
Yeah.
The A what?
It's A prime and A double prime.
Okay.
Yeah, sorry.
That's not your fault.
A double prime, and that's A prime. That's just two different, I'm just using that to denote two different values of A. Let me do a different one. How about Solow neutral technology. Solow neutral technology is sometimes referred to as capital augmenting. It looks a little different. Imagine you have a production function, again, F tilde, that's a function of capital, labor, and technology, where its constant returns to scale in K and L. This production function has a Solow neutral technological progress, or capital augmenting technology, if you can rewrite it as F of A times K times L. In other words, technology in this production function more or less augments the capital stock as opposed to labor. Okay, if we were to look at this on an ISO production schedule, here's L, here's K, here's Y bar of A prime, okay? If there is an improvement in technology that shifts the ISO production schedule down, we can now produce the same amount of output using less capital, but the same amount of labor. That's what, so in other words, technology here has augmented the capital stock. So we can produce the same amount of output using less capital, but it requires the same amount of labor as when technology was A prime. That's what Solow neutral or capital augmenting technology looks like. It doesn't affect labor directly, but rather it improves the efficiency with which you use the capital stock.
Is there a reason why it doesn't just pivot?
Oh, you mean like
a tap? Yeah.
Like this?
Yeah.
That's not a big deal.
Okay.
Yeah, I sort of drew it that way a little bit, but yeah, in fact, on my notes, I have it kind of coming in like that a little bit. But the idea here is that technology doesn't allow you to conserve on labor if you want to produce the same amount of output. It allows you to conserve on capital, because capital is becoming more efficient. Obviously, that leads to a third type of technology, which these all go by the name of famous economists, by the way. So this one is Herod, neutral technology. And this is a type that augments labor as opposed to capital. In this case, F tilde can be rewritten as F of K A times L. So an improvement in technology more or less just augments the supply of labor. Labor becomes more efficient as opposed to the capital stock. In that case, the ISO production for schedule would kind of pivot, using Ben's language here, counterclockwise with higher technology, which allows us to conserve on labor using the same existing amount of capital. That's labor augmenting as opposed to capital augmenting. You might also imagine a fourth type of technology, which we'll just call a mixture. This is conceivable, right? Imagine technology actually being a vector valued object that has a Hicks neutral component, a Solow neutral component or capital augmenting component, as well as a Herod neutral or labor augmenting component. So imagine technology actually was a vector of 3 dimensions. In that case, we can think about F tilde as being equal to AH times F of a k times k, a l times l. All four of these forms of technological progress look equally plausible, right? There's no reason to think that one of them is more realistic or more empirically compelling than another. But it turns out that if we want our growth model to exhibit the property of balanced growth in the long run, then all technological progress has to take a particular form. It has to be labor augmenting, Herod neutral. Now, it's not going to be really obvious right now why that's the case. We're going to work through the proof of Uzawa's theorem to hopefully provide some intuition. But all types of technological progress have to be expressible as labor augmenting technology in order for the production function inside the growth model to exhibit or predict a balanced growth position. That sounds like it's really restrictive. That sounds like it possibly rules out any of these other types of technology. Well, be careful about that. In the class of production functions that macroeconomists use most to model things, which is the so-called Cobb-Douglas production function, you've probably seen in some of your review questions, right? Y is equal to k to the alpha times L to the 1 minus alpha. That's a special class of production functions whereby even if you have capital augmenting or Hicks neutral, through a clever change of variable, you can rewrite that production function in terms of just labor augmenting technology. So it is not necessarily the case that a type of technology that's not labor augmenting is inconsistent with balanced growth. You just have to do a quick change of variable in the class of Cobb-Douglas production functions to make it look like it has labor augmenting technology. If I have time after the proof, I'll give you a demonstration of that. You may have already seen one in one of the review questions that we've done. Okay, so that's what I want to emphasize, is that although this sounds really restrictive, that everything has to be labor augmenting, in most actual applications in the research, if we use something like a Cobb-Douglas production function that multiplies the two inputs together, you can move around that technology term to make it look like labor augmenting technology. Okay, any questions yet? Let's that brings me then to the main task for today's talk, and that is a proof of Uzawa's theorem, Theorem 3 in your notes. All right, what does Uzawa's theorem say? Let's talk about this very clearly so that we can interpret what it's saying here. Let's consider a growth model, any growth model. It does not have to be the Solow growth model. Any growth model that has an aggregate production function of this form. Output is equal to F tilde, and its three arguments are physical capital, labor, or the population, and technology, which I'll call A tilde. The function F tilde, we're going to assume maps elements of R2 times script A into the positive reals, where A tilde is just an element of script A. So this script A is just an arbitrary set that the technology variable belongs to. I'm not going to make any other real assumptions about what script A looks like. All right. So the production function maps elements of R2 times script A into the positive reals. F tilde is going to exhibit constant returns to scale in its first two arguments. So it's got to be linearly homogeneous with respect to K and L. That we've assumed from the get-go. Moreover, the growth model that we're dealing with exhibits an aggregate resource constraint of the following form. The change in the capital stock between periods t and t plus 1 is equal to the economy's production of output minus total consumption minus how much of the capital stock depreciates. Again, this is just the evolution of the capital stock in the Solow model. Y minus C is investment, right? So investment minus depreciation is how much the capital stock grows from t to t plus 1. This equation is going to be in most of the models that we look at. It's not unique to the Solow model. All right, we're also going to suppose here that population growth is constant. So LT is equal to 1 plus N LT minus 1. We are also going to assume that there exists some period cap t less than infinity, such that for all little t bigger than or equal to cap t, output, consumption, and capital are all growing at constant rates. So once we move out far enough into the future, we're going to be at a point where output can be written as 1 plus gy times yt. Kt plus 1 can be written as 1 plus gk times kt, and ct plus 1 can be written as 1 plus gc, let's call it, times ct, where these growth rates, gy, gk, and gc, are all bigger than 0. That's the last part of the assumption of the Uzawa's theorem, is that eventually we're going to reach a point in our growth model where output, consumption, and capital are growing at constant rates. And so the value of output next period is simply equal to 1 plus the growth rate times the value of output today. Okay? These are the assumptions of Uzawa's theorem. If those assumptions hold, and again, this is not unique to the Solow model, but rather to a huge class of growth models, then the following two things must be true. That the growth rates of output, capital, and consumption are equal to each other. Let's just call it G. In other words, we have balanced growth. The second and critical part of the theorem says that for all t bigger than cap t, there exists some function f that maps elements of R2 into the positive reals, that is homogeneous of degree 1 in its two arguments, such that our production function f tilde can be represented as f of k t a t l t, where at is an element of the reals and at plus 1 is equal to 1 plus, let's call it GA times AT, where GA is equal to 1 plus G over 1 plus N. Now, let me stop there and make sure everybody can interpret or digest what I've just said. If the production function is constant returns to scale in capital and labor, if it exhibits this resource constraint, which is standard, has constant population growth, and if output, capital, and consumption eventually grow at constant rates, then it must be true that those growth rates are the same, that is, the model exhibits balanced growth, and most importantly, the production function f tilde has a form that must be represented in terms of labor augmenting technology. So balanced growth requires labor augmenting technological growth, where technology is some element of the reals. And the growth rate of technology is directly related to the growth rate of output, capital, and consumption, as well as the population growth rate. Can we prove it? Sure we can. We're going to prove it in 2 steps. We're going to prove part 1 and then prove part 2. Let me write output at date t to be equal to 1 plus gy raised to the t minus cap t times y at cap t. Everybody see how I got that? For t larger than cap t, we're at a point where output is growing at a constant rate. So y little t is simply going to be equal to y cap t times 1 plus g raised to the power of the time that is elapsed between little t and big T. K little t is similarly just 1 plus gk raised to the t minus cap t times k cap t. All right? Yt plus 1 is just 1 plus gy times yt. So what is yt plus 2? It's 1 plus gy squared times yt. Yt plus 3 is 1 plus gy cubed times yt, et cetera, et cetera. Ct is just 1 plus gc to the t minus cap t times c cap t. And again, this is for all t bigger than or equal to cap t. That's our hypothesis. All right. So for any t bigger than or equal to cap t, I'm going to rewrite the aggregate resource constraint up here in terms of my transformed variables. So for instance, kt plus 1 minus kt, what is that going to be equal to? Well, kt plus 1 is just 1 plus gk times kt minus kt. What was the right-hand side of the resource constraint? It's y minus c minus delta k. So yt is just 1 plus gy to the t minus cap t y cap t minus ct, that's 1 plus gc to the t minus cap t c cap t, and then minus a delta kt. Some things cancel here, right? I've got a kt minus a kt, so that one's going to cancel with that one. And if I bring this delta kt to the left-hand side, I get gk plus delta times kt. Well, what is kt? That's 1 plus gk to the t minus cap t times k cap t is equal to this stuff I have on the right-hand side. All right, now what I want to do is divide both sides of this equation by this term here, 1 plus gk raised to the t minus cap t. And I will be left with gk plus delta times k cap t is equal to 1 plus gy over 1 plus gk raised to the t minus cap t times y cap t minus 1 plus gc over 1 plus gk raised to the t minus cap t times ct. All right, everybody follow how I got that? So remember, this equation has to hold for any little t bigger than cap t. So cap t is this fixed position. That's the point at which these variables are growing at constant rates, right? The time dimension here is represented by the little t. All right, now here's what I want to do. I want to do a trick. And not all of this stuff, none of this is really obvious, but this is how we're going to prove it. What I want to do is I want to first difference this equation. You guys know what that means? When you first difference a difference equation, let's say you have xt is equal to yt. If you take that equation in first differences, then what you do is you subtract from both sides of that equation the value of those variables one period earlier. So if xt is equal to yt, then it should be that xt minus 1 is equal to yt minus 1. Right? So that's what I want to do to this equation is I want to evaluate it at date t, and I want to subtract from that equation the same thing evaluated at date t minus 1. Cap t is being held fixed here. The time dimension is reflected by lowercase t. All right. Now, the left-hand side, because we've moved stuff around here, actually doesn't depend on little t, does it? So if we first difference the left-hand side, what do we get? gk plus delta times k cap t minus the same thing, it's going to give us 0, right? So the first difference of the left-hand side is equal to 0. What's the first difference of the right-hand side, though? That's a little different, right? Because the little t's are right here and here. So we've got to be careful about how we write this. This becomes 1 plus g over gy over 1 plus gk t minus cap t, y cap t, minus the same thing evaluated at date t minus 1. Minus 1 plus gc over 1 plus gk raised to the t minus cap t ct, plus, because that term enters in with a negative sign, so when you subtract it becomes positive, 1 plus gc over 1 plus gk raised to the t minus 1 minus cap t ct. That's what happens when we take first differences of this equation. I think your textbook author does a proof of Uzawa's theorem in continuous time, if I'm remembering right, that can take derivatives with respect to t. We obviously can't do that. We have to take differences. All right, let me simplify this a little bit. There's a common term here that we can factor out. 0 should be equal to, let me factor out a 1 plus gy over 1 plus gk raised to the t minus cap t. What you're going to be left with from the first two terms there is a 1 minus this ratio of growth terms to the -1. So if we combine those together, you get gy minus gk over 1 plus gy, obviously times y cap t. You can group the same type of terms that are attached to these consumption values. So minus 1 plus gc over 1 plus gk raised to the t minus cap t times gc minus gk over 1 plus gc times c cap t. This must hold, again, for all t bigger than or equal to cap t. Now, you may not be able to quite see all the steps of algebra there, but I assure you that if you factor out this ratio to the t minus cap t, you'll be left with a term that collapses to gy minus gk over 1 plus gy. And that's all that'll be left. And the symmetric thing for consumption. Okay, we're almost able to prove the first part now. In order for this equation to be equal to 0, one of 4 cases must be true. Case 1. The only way for this equation to be equal to 0 would be for gy to be equal to gk, right? If gy was equal to gk, that's equal to 0. And if gy is equal to gk, it's also equal to gc. So if the growth rates were all equal, as the first part of this proof suggests, then the first term is 0 and the second term is 0, and the whole expression is equal to 0. That's certainly one way for that equation to be true. And that will turn out to be the only one that's possible. But there's a couple of other ways that this equation could be 0, right? What if instead gy was equal to gc? So gy and gc are the same. So this term over here and this term over here are equal except for y cap t and c cap t. Well, if y cap t is equal to c cap t, then the right term and the left term are equal, and the whole thing is equal to 0. So that's certainly another way for that equation to be equal to 0. A third way could be for gy to be equal to gk, and then for c cap t simply to be equal to 0. That way the left and right hand terms are going to be 0. And then the last way that I see is possible is if gc is equal to gk, and instead y cap t is equal to 0. If this difference equation that we've derived is going to be equal to 0, one of these 4 things must be true. And what we want to do is show that 3 of them are inconsistent with some assumptions we've made about the model, leaving only 1 to be true. And you might imagine that one that's going to be true is the first one, where the growth rates of all 3 variables have to be the same. All right, let's start with number 2. Why is number 2 not possible? Well, let's think about this. If gy is equal to gc and c cap t is equal to y cap t, go back to this sheet here. If gy is equal to gc and y cap t is equal to c cap t, then that tells us that yt is going to be equal to ct forever, right? So case 2 implies that yt is equal to ct for all t bigger than or equal to cap t. But if yt is equal to ct, then that means that kt plus 1 minus kt is simply equal to negative delta kt. That's from the resource constraint. Yt is equal to ct, then the change in the capital stock is just negative delta times kt. Which means that the growth rate of capital would simply be equal to negative delta, which is a negative number. And that can't be true because we've assumed that the growth rate of the capital stock is positive, right? G sub K has to be a positive number. So case 2 can't be true. That's inconsistent with having a positive growth rate for capital. How about case 3? If GY is equal to GK and C cap T is equal to 0, then this would imply that CT is going to be equal to 0 for all T greater than or equal to cap T. Remember, once we've reached a point where consumption is growing at a constant rate, if we set C cap T to 0, then that simply means that CT is going to be 0 forever, right? And if CT is 0 forever, that means the growth rate of consumption is 0. But we know that's not true because it has to be positive. So the growth rate of capital has to be positive and the growth rate of consumption has to be positive. Same with case 4. Case 4 has y cap t equaling 0. Well, that would imply then that y little t is equal to 0 for all t bigger than or equal to cap t, which would imply that the growth rate of output is 0. That's also inconsistent with our assumption. So cases 2, 3, and 4 can't be true because all of them imply that the growth rate of capital, consumption, and output are either 0 or negative. There's only one of those 4 cases that is consistent with positive growth rates of those 3 variables, and it's the case in which the growth rate is the same across all of them. So the model or the production function must be consistent with balanced growth. Now, how can we demonstrate that the production function must have a representation consistent with labor augmenting technology? That's the second part of the proof here. Okay, let me start off by writing output at date cap t as the following. It's our production function f tilde of k cap t, l cap t, and I believe it was a tilde cap t. That's the production function that we're dealing with in this hypothetical model. And remember, the production function must hold for any time, all right, including this date cap t at which all the variables start to grow at constant and equal rates. For any t bigger than cap t, then, I should be able to write this particular production function at this particular date, cap t, as the following. 1 plus gy raised to the negative t minus cap t times y little t is equal to f tilde. What is k cap t? Well, that's 1 plus gk raised to the negative t minus cap t times k little t. And L cap t can be written as 1 plus n to the negative t minus cap t times L little t. And then we can't forget about the A tilde cap t. I'm not sure why that's not showing up very well, but can you guys see that okay? So just to be clear, where does that come from? So we went from here to here. K cap t or Y cap t. I'm just inverting these equations, right? Y cap t is YT times this thing raised to the negative T minus cap t. So I'm just turning these equations on their heads and using those to substitute them into the production function. Okay. Now, what do we know about F tilde? It has constant returns to scale in its first two arguments, right? So what I'm going to do is I'm going to multiply both sides of this equation by 1 plus gy raised to the t minus cap t. So that the left-hand side is just y little t. When I do that, I can, this is just a scalar, right? And I can shove this into the production function because F tilde exhibits constant returns to scale. So this becomes F tilde. And what is 1 plus gy raised to the t minus cap t times 1 plus gk raised to the negative t minus cap t? Well, that's just 1 plus gy over 1 plus gk raised to the t minus cap t times kt. And then I've got a 1 plus gy over 1 plus n raised to the t minus cap t times lt. And then we can't forget about the A tilde. Now, what do we know about gy versus gk? From part one of our proof, we proved that gy was equal to gk, right? So this whole term here is just 1. So yt is equal to f tilde kt. Isn't this looking nicer? You can write yt as a function of kt and something times lt. That something to me looks like labor augmenting technology, and L tilde. Now let us define a technology parameter at as the following. I'm going to define this as 1 plus gy over 1 plus n times at minus 1. So at grows at this constant rate, 1 plus gy over 1 plus n. Well, that implies then that at should be equal to 1 plus gy over 1 plus n raised to the t minus cap t times a cap t. And that must be true for any t bigger than or equal to cap t. Therefore, a t over a cap t is just equal to 1 plus gy over 1 plus n raised to the t minus cap t. Now let's plug that back into the production function here. And we get that yt will be equal to f tilde kt. Now 1 plus gy over 1 plus n raised to the t minus cap t is just at over a cap t. Well, that's just equal to a function of kt, atlt, and then there are two terms that are independent of little t. So we can just write them as secondary arguments. And there we go. We can simply write that as a function then of kt and atlt, because a cap t and a cap tilde cap t are independent of little t. And again, that's for all t bigger than or equal to cap t, where the growth rate of labor augmenting technology here is equal to 1 plus gy over 1 plus n, which is exactly what was in the statement of Uzawa's theorem. So balanced growth, along with our basic assumptions about production and the resource constraint, implies that technology must take the form of this labor augmenting type. And again, this was stated and proved without reference to any specific model. So it's true of any model that exhibits a neoclassical production function, whether it's the Solow model or the overlapping generations model or an optimal growth model or whatnot. It shows that in order for the model to be consistent with balanced growth in the long run, that is, the main endogenous variables are all growing at constant and equal rates, that the production function must take on a form that exhibits labor augmenting technology eventually. That is, for t greater than or equal to cap t. So if all of those assumptions of Uzawa's theorem are satisfied, then technological progress can be represented as Herod neutral. That's what the last corollary is, or purely labor augmenting. So Uzawa's theorem doesn't provide a reason for why technological growth must be of the labor augmenting form. It merely says that in order for the model or for the production function to exhibit balanced growth or be consistent with balanced growth, technological progress must take the labor augmenting form. Now, one last thing I want to say before we finish today is that although this sounds really restrictive, it need not be. In the class of production functions, for example, that is Cobb-Douglas, let's say we have a mixture technology that has a capital augmenting component and a labor augmenting component. So let's say our production function looks like this. Now you might glance at that and say, well, technology doesn't take the labor augmenting form, and so there's no way you can get balanced growth. Well, not so fast. In a Cobb-Douglas world, we can rearrange these technology terms in order to make it isomorphic, if you will, to labor augmenting technology, right? What is this equal to? This is just kt to the alpha times a kt to the alpha times a lt to the 1 minus alpha times lt to the 1 minus alpha. Well, how can I get this composite technology term inside of the production function attached to L raised to the 1 minus alpha. In other words, make it look like labor augmenting technology. Well, that's pretty straightforward. We can write this as what? A kt to the alpha over 1 minus alpha times a lt to the 1 times lt raised to the 1 minus alpha, right? All we've got to do is define a new technology variable, at. Let's define it as a kt to the alpha over 1 minus alpha times a lt. If we define at as that, then the production function becomes y is equal to k to the alpha times at lt to the 1 minus alpha. Where you just have to be careful, the growth rate of at will depend on the growth rates of al and ak, and will also depend on alpha. But it still takes the labor augmenting form. You guys see what I'm saying there? Is that with a Cobb-Douglas production function, you can quite often rearrange it or do a quick change of variable to make technology look like labor augmenting. And once you do that, then the model has a balanced growth path. Now, you may have already seen this in some of the problems you've been working, but the way to solve these models to make the variables stationary is you want to work with not capital per worker and output per worker, right? What you want to do is you want to normalize your variables by ATLT, that is capital and output per effective worker. So define your stationary variables as per effective units of labor. And when you do that, you'll see that all of the equations of the Solow model that we've talked about in class carry through. And what you'll find is that output per effective worker, little y, will reach a steady state. Well, what does that mean about output per worker? It'll be equal to YT times AT, correct? In the long run, little y goes to y star, but output per worker will still grow at the same rate as exogenous technological progress. That's how your growth models generate sustained growth in the long run, is you've got to incorporate technology. Okay, folks, that is all I have on the Solow model. Really, today's discussion wasn't really so much on the Solow model as it was on an important theorem regarding the neoclassical style production function. Let's see, is today Wednesday? Next Wednesday, we have Monday off because of Labor Day, right? So next Wednesday, we'll pick up and start our first new topic is going to be overlapping generations models. I'm guessing that's going to take at least 4 classes to get through. That class of models is different than the Solow model because we're going to actually endogenize the savings consumption decision of households. In that model, we're going to have households of different generations interacting with one another in markets. Some people will supply labor, others will supply capital, markets will clear. There's an endogenous savings mechanism that determines how capital evolves over time. So it's more complicated than the Solow model, but it's going to build on some of the stuff we've seen. We'll set the model up and kind of talk about it in general the first day, and then we'll do the same kinds of things we did for the Solow model. We'll discuss whether or not the model admits a steady state, whether that steady state is stable, what do the transition dynamics look like. The overlapping generations model provides a convenient framework to analyze intergenerational fiscal transfers. So things like Social Security, where you tax young workers and you use that to provide lump sum transfers to people who are retired. So we'll spend some time talking about fiscal policy in the context of that model and how those types of tax and transfer systems can cause the steady state to move in an efficient or an inefficient direction. One of the key reasons why we talk about the OLG model is because it provides a nice example of a model that has endogenous consumption and savings behavior, where you still have certain externalities that are embedded in the model, whereby the competitive outcome is not necessarily the socially optimal outcome, where the invisible hand principle breaks down. We'll talk about the nature of those externalities, and then how these fiscal transfers can unwind those distortions or externalities to some extent. All right, but that'll be towards the back end of the presentation. I'm assuming it'll take about 2 weeks to get through, and then we'll talk about when your first exam is going to be. Okay, Tavoy, are you good? Do you have any questions?
Good so far. Thank you,
Okay.
sir.
All right, we will call it a day then. See you guys.